Good afternoon. My name is Tim Miller, and I'm responsible for the product management at NET. Today, we introduce you how you can use smart vision technology to create your embedded system. NET is part of the TKH group, which is listed on the stock exchange with an annual turnover from 1.5 billion euro. The Vision Group, with a turnover of 200 million, consists of 8 companies and also includes Allied Vision, who are the third speaker today. Especially in the medical field, we can look back on 25 years of experience in embedded vision systems. We can proudly say that our camera systems make the work of the physicians easier, safer, and more accurate in many operating rooms around the world, and reduce the stress of an operation for the patient by using the smallest image sensors with an image enhancement algorithm by NET. Since the start of our latest GigiVision camera in 2013, which already allows customer-specific pre-processing, we mainly offer our camera systems to our customers. In addition to our core business of camera technology, NET has a strong expertise in optical components. We design and calculate optical systems for the special applications of our customers, but we also have over 1,000 different standard optics, such as telecentric lenses, in our portfolio. You can get more information about our optic business in our contribution to the InVision Tech Talk on the March 16. The requirements for an embedded system are and always have been very high. In addition to the poor functionality and processing power, the various applications also have very different requirements. These requirements for an embedded system arise from the most varied applications. Today, in our presentation, we take a closer look at 3 samples. In factory automation, the decisions are made on-site. Image data is usually no longer transmitted. Instead of that, control units such as motor controls are addressed directly. Vision systems are used to find the location and position and to recognize the objects for the robot controller, for example, in pick-and-place systems. In both cases, it is important to have the right interfaces to the PLC and the host computer. In the medical field, embedded systems are used in 3D scanners to produce dental implants precisely. For this, up to 4 cameras are required, which carry out a 3-dimensional recording with structured light. Not all of the data is transferred to the CPU. The point cloud is already generated in the FPGA part of the embedded vision system. In agriculture, it is mainly about recognizing objects and defining their type and position. If you work with natural objects and shapes such as plants, edge systems with artificial intelligence becomes more and more important to the infinity number of variations. In order to process neural networks on an embedded system, hardware acceleration, for example, on an FPGA is necessary. Embedded vision system consists of many different components. Each of these squares represents a property of the components. The difficulty is to get the best possible performance out of this multitude of different components with different individual properties. The performance of an embedded system depends very much on how well an individual component works together. Selecting the right sensors, you can fall back on a large number of technical features such like resolution, frame rate, or spectral sensitivity. Some of the interfaces are standard, like the USB 3 Vision or the well-known GigiVision. Even these standards cannot be simply exchanged. The sensors have interfaces such as MIPI or LVDS, and every manufacturer has its own particularities in interpreting this standard. The heart of the embedded system is the CPU, which of course also influences the selection of the operating system. For the operating system, you have to consider whether it is up to date or compatible with the previous models. There are different operating systems such as Windows, Linux, iOS, or Android that have to match the software you want to use. If we put these variables together, there are combinations that fits optimally. In this case, we see that the combination of an Intel CPU fits perfectly with the Windows operating system. An ARM processor as a CPU would be a very unusual combination right now. Some combination fits with restrictions, and in the worst case, some of them can only be brought together with a great effort. Here we see the requirement to use an Android system. The combination of an ARM with a DSP is less flexible. An ARM and FPGA combination would have been the better and more flexible choice here. In the last pages, we saw that an intelligent camera system or a complete image processing system has emerged from many different puzzle pieces. Our core site put these puzzle pieces perfectly together. A large variety of sensor types is supported from matrix sensors with VGA up to 5 megapixel and line scan sensors with 2K and 4K. This can be used to solve many applications, from reading codes through inspection solutions up to continuous scanning on a conveyor belt. One of these sensors is the Luxima 1310 with 1.3 megapixel and over 1000 frames per second. If 1000 frames per second are not enough, the resolution can be reduced and up to 1 million frames per second can be reached in line scan mode. You can solve applications such as laser triangulation, which require a very high frame rate. CoreSight support optics with C-mount or S-mount. Here you can rely on our large selection of optics. Inside the lens tube works an optional IR or white LED ring. The high read rate is pre-processed in the Xilinx Arctic 7 FPGA and is transferred to the CPU via the internal PCI Express bus. The Intel quad-core Atom processor can run Windows 10 IoT or a Linux distribution. This combination fits together very well. Our open camera concept also includes a framework that allows our customer to access the resources of the FPGA by themselves. In the same time, it is possible to use a variety of software you are already used to on PC-based systems. Our customer work with software development in-house based on OpenCV or use image processing libraries such as Emitech Halcon, Matrox Mill, or Adaptive Vision Studio. As an interface to the machine or as a human-machine interface, CoreSight offers RS-232, USB, DisplayPort, wireless or Bluetooth, GigE, and digital input-outputs, for example, to directly connect an incremental encoder to the system. We have packed the complete embedded system in an IP67 housing with a fanless temperature management. CoreSight is a completely engineered smart vision system ready to go. No matter what configuration you use, CoreSight is an optimally configured system. Our newest smart vision system, IM, fits to a wide range of applications as an integrated smart vision solution and allows decentralized image processing on an edge device. The flexibility in hardware and software opens up new possibilities to grow with the future requirements. A flexible lens mount with S-mount and 12 size, C-mount is the most widely used mount. F-mount for bigger sensors or line scan sensors will be available soon. Right IM offers high-resolution image sensors from VGA to 12 megapixel rolling and global shutter. Most of them are the popular Sony IMX sensors, which are widely used in the industrial vision market. Line scan sensors, like we use in our CoreSight, are under development. Multi-sensor applications, up to 4 image sensors, are possible. For example, for stereo vision application with a hardware acceleration on the FPGA. The housing with an industrial design take care of an efficient temperature management. The ultra-scale SoC CPU contains a quad-core ARM CPU and an FPGA in one chip. Many of your vision tasks can be hardware accelerated on the FPGA. For example, a neural network can be accelerated with Xilinx Whitey's DPU on the FPGA. The system is equipped with a Jiggy Vision server and allows plug-and-play use like with any standard Jiggy Vision camera. There are digital input-outputs available for machine control, for example, to work with an incremental encoder. Our open camera platform allows customers to access the FPGA and the ARM processor. With the Xilinx Whitey's United Software Platform, you can use the resources of the FPGA without any knowledge about hardware description language like VHDL or Verilog. It has never been so easy to use hardware acceleration. Beside in-house development algorithms, standard software libraries from the market are also work on IM out of the box. Future interfaces, depending on customer requirements, are planned, like Feldbus, Profibus, CAN bus, or EtherCAT, 5G network, or USB 3. Like CoreSight, IM is a completely engineered smart vision system ready to go. IM reduced your time and development effort in order to reach your goal for an embedded system. If we summarize this, using our ready-to-go smart camera system, we showed you how an embedded system is put together from a complex building block. The smart vision system IM and CoreSight take this complexity out of your hands. You can now generate your vision solution based on this finished concept. The wide variety of sensors will help you with almost every vision task. The perfect interaction between the operating system and the CPU allows maximum performance. Our open camera concept allows customers to access the CPU and the FPGA. And with the Xilinx Whitey's United Software Platform, you can use the resources of the FPGA on IM without any HDL design knowledge. As we can see on the next page, in addition to our open system, we also adapt the hardware according to your needs. We can see very well how our standard camera IM on the left side becomes a customer-specific solution on the right side. The cooling concept was adapted to the mechanical conditions. The interface board has not been functionally changed, but has been adapted to the mechanical conditions. The LED control was added. The standard Ethernet connector became an M12 connector. The main board remained unchanged and was rotated by 90 degrees. The sensor board remains the same, only the connections are adapted to the rotated main board. The optical mount was unchanged. A new customer-specific variant has been created and has an independent customer design. In addition to the main components, many others have significant influence on the success of an embedded system. In order to communicate with the machine controls or to implement an HMI, interfaces are necessary. Starting with the optics, cables, lighting interfaces for machine control, mechanical connections, additional measuring devices, software tools to use hardware acceleration, image processing software, and custom applications with integrated HMI. All these components are part of the overall image processing system. On the first part of this presentation, we showed you 3 application cases of embedded vision systems, which we will now explain in more detail. Factory automation and robotic. Here we see a typical pick-and-place application. The vision system is integrated and has a central task here. The customer's PLC sets the pace via a digital interface. The belt speed recorded directly by the vision system via an incremental encoder. The smart camera or the embedded system registers and measures the position of the object on the conveyor belt. The position is then transferred to the robot controller, which is, with this information, the robot picks up the parts and sorts them, for example, into the right packaging. As you can see, the system works hand in hand with the corresponding interfaces to the PLC and to the robot controller. The software platform of these three systems must also work hand in hand. Our open camera system supports customer-specific requirements, and you have all the options. Here we see the principle of a 3D scanner for dentures. For the three-dimensional measurement, a stripe pattern is projected onto the object. The structured light stripes change their position and the distance from frame to frame. The projector is controlled by the vision system. The position of the stripes is also influenced by the third dimension of the object and recorded by one or more sensors, in our case with 2 sensors. The image is analyzed and the embedded system and the data is transferred to a computer system as a 3D point cloud. Most manufacturers of 3D scanners use their own software. Thanks to our open camera concept, this customer is also able to design their own individual system based on our smart camera system. In this example, we show you a project with segmentation. Various natural shapes such as trees, grass, animals, or the sky are taken into account and used to train a neural network. The network is trained with the TensorFlow framework. With the WITES United Software Platform, the trained neural network will be prepared for accelerate use on the hardware that's called DPU. The trained network is uploaded to the vision system for processing. The vision system, IM Machine Learning Ready, is already equipped by NET with optimized hardware acceleration, the DPU on the FPGA. Customers who want to transfer their own neural networks only need to transform them in an automatic process. The position of the objects in the image can be determined to segmentation. In this case, an agriculture machine can become autonomous. It can also be used to distinguish between weeds and crops and control the various tools such as a cutting device. Beside the hardware acceleration, the vision system takes over the complete application control. In the last 20 minutes, we show you how you can benefit from a ready-made smart vision solution and still remain flexible. For more detailed information, we invite you today to join our roadshow all across Germany in mid of April. With our quick start guide, we will show you how you can take the first steps. We will also show you how you can use your own software to integrate vision libraries. We show you how to use open source tools and what possibilities the Xilinx WITES platform offers. We show you how you can accelerate a neural network for the IM smart camera. With our open camera concept, you can also use the resources of the FPGA. You don't need any HDL programming or design knowledge for that. I look forward to meet you personally at the roadshow in the mid of April. You will find all the data and book a seat on our homepage, net-gmbh.com. Thank you for your attention. I'm ready now.
Thank you, Tim, for your presentation. And now it's the time for your questions. Once again, please use the Q&A section. And there's already the first question. How far is the access of the user to the FPGA given? Can this be done by the user or needs this to be done by NET?
We use the Xilinx WITES platform for this. For example, if you use now OpenCV algorithm, you can find this algorithm hardware accelerated for ultra-scale architecture in the WITES platform. is the same for neural networks. There you will find pre-trained networks that have already been optimized for the hardware acceleration.
So, and how can you perform hardware acceleration on the FPGA if you do not have HDL knowledge?
Yes, that's possible. We also use for this the Vitis platform. They offers this. They have pre-trained networks, what you can retrain, and then you can put it on the IM, and the IM is already installed on DPU for hardware acceleration on the FPGA. And this can be done by the customer without knowing the VDHL coding.
Mm-hmm. And next question, is it possible to use your embedded system with Halcon? Also Halcon software from MVTech?
Yes, that's possible, of course. Yeah, with our open camera concept, we have created the possibility that our customers can use their usual software. In addition, we offer a framework to use the resources of the FPGA. We have already explained this. But our customer also want to use this Halcon, for example, and we have pre-installed, or we can pre-install such libraries. We, for ourselves, have, for example, the adaptive vision library in our program. So that's also possible.
Okay, time's running by, so one last question. There will be another Q&A section after the last presentation. So maybe you have then new questions. Why do you have a Gigi vision server running on your smart camera?
Yeah, the image processing system presents itself to the outside as a simple Gigi vision camera. For example, optical settings can be made very easily during the installation. Gigi vision also offers a high performance image data transfer if this is required. In addition, inspection results can also be transferred via Gigi vision. This is an additional feature that can be switched on and off at any time, for example, for service proposals. So that's why we are also using the Gigi vision server.
Okay, thanks a lot.